Extensions to the maximum flow problem. Much of the power of the maximum flow problems has essentially nothing to do with the fact that it models traffic in the network. Rather, it lies in the fact that many problems with a non-trivial combinatorial search component can be solved in a polynomial time because they can be reduced to the problem of finding a maximum flow or a minimal cut in the directed graph. Bipartite matching is a natural first application in this vein. In the coming sections, we investigate a range of further applications. To begin with, we stay with the picture of flow as an abstract kind of traffic and look for more general conditions we might impose on this traffic. These more general conditions will turn out to be useful for some of our further applications. In particular, we focus on two generalizations of maximum flow. We will see that both can be reduced to the basic maximum flow problem. The problem, circulations with the demand. One simplifying aspect of our initial formulation of the maximum flow problem is that we had only a single source S and a single sink T. Now suppose that there can be a set S of sources generating flow and a set T of sinks that can absorb flow. As before, there is an integer capacity on each edge. With the multiple sources and sinks, it is a bit unclear how to decide which source or sink to favor in a maximization problem. So instead of maximizing the flow value, we will consider the problem where sources have fixed supply values and the sinks have fixed demand values. And our goal is to shift flow from nodes with available supply to those with given demands. Imagine, for example, that the network represents a system of highways or railway lines in which we want to ship products from factories, which have supply to retail outlets which have demand. In this type of problem, we will not be seeking to maximize a particular value. Rather, we simply want to satisfy all the demand using the available supply. Thus, we are given a flow network G equals to V with the capacities on the edges. Now associated with each node little v in capital V is a demand dV. If dV is greater than 0, this indicates that the node V has a demand of dV for flow. The node is a sink and it wishes to receive dV units, more flows, then it sends out. If dV is less than 0, this indicates that V has supply of minus dV. The node is a source, and it wishes to send out minus dV units, more flow, than it receives. If dV is equals to 0, then the node is neither a source nor a sink. We will assume that all capacities and demands are integers. We use S to denote the set of all nodes with a negative demand and T to denote the set of all nodes with a positive demand. Although a node V in S wants to send out more flow than it receives, it will be okay for it to have flow that enters on incoming edges. It should just be more than compensated by the flow that leaves V on outgoing edges. The same applies in the opposite direction to the set T. In this setting, we say that a circulation with the demands, the set dV, is a function f that assigns a non-negative real number to each edge and satisfies the following two conditions. 1. Capacity conditions. For each little e in capital E, we have 0 less than equals to f of E less than equals to CE. 2. Demand conditions. For each little v in capital V, we have V f to the in of V minus f to the out of V equals to dV. Now, instead of considering a maximization problem, we are concerned with a feasibility problem. We want to know whether there exists a circulation that meets conditions 1 and 2. For example, consider the instance in figure 7.13a. Two of the nodes are sources, with demands minus 3 and minus 3. And two of the nodes are sinks, with demands 2 and 4. The flow value in the figure constitute a feasible circulation, indicating how all demands can be satisfied while respecting the capacities. If we consider an arbitrary instance of the circulation problem, here is a simple condition that must hold in order for a feasible circulation to exist. The total supply must equal the total demand. 7.49 If there exists a feasible circulation with demands the set dV, then the summations of dV summing for all v is equals to 0. Proof: suppose there exists a feasible circulation f in this setting, then the summations of dV summing for all v is equals to the summations of f to the in of v minus f to the out of v summing for all v. Now in this later expression, the value f of e for each h little e equals to uv is counted exactly twice, once in f to the out of u and once in f to the in of v. These two terms cancel out, and since this holds for all values f of e, the overall sum is 0. Thanks to 7.49, we know that the summations of dV summing for all v such that dV is greater than 0 is equals to the summations of minus dV summing for all v such that dV is less than 0, and let d denote this common value. Designing and analyzing an algorithm for circulations. It turns out that we can reduce the problem of finding a feasible circulation with demands the set of dV to the problem of finding a maximum ST flow in a different network, as shown in figure 7.14. The reduction looks very much like the one we used for bipartite matching. We attach a super source S star to each node in S and a super sink T star to each node in T. More specifically, we create the graph G prime from G by adding new nodes S star and T star to G. For each node V in T, that is each node V with dV greater than 0, we add an HV T star with a capacity dV. For each node U in S, that is each node with a du less than 0, we add an HS star U with a capacity minus du. We carry the remaining structure of G over to G prime unchanged. In this graph G prime, we will be seeking a maximum S star T star flow. Intuitively, we can think of this reduction as introducing a node S star that supplies all the sources with their extra flow, and a node T star that siphons the extra flow out of the sinks. For example, part B of figure 7.13 shows the result of applying this reduction to the instance in part A. Note that there cannot be an S star T star flow in G prime of value greater than D, since the cut AB with A equals to the set S star only has capacity D. Now if there is a feasible circulation F with demands the set dV in G, then by sending a flow value of minus dV on each H S star V and a flow value of dV on each H V T star, we obtain an S star T star flow in G prime of value D, and so this is a maximum flow. Conversely, suppose there is a maximum S star T star flow in G prime of value D. It must be that every H out of S star and every H into T star is completely saturated with flow. Thus, if we delete these H's, we obtain a circulation F in G with a F to the in of V minus F to the out of V equals to dV for each node V. Further, if there is a flow of value D in G prime, then there is such a flow that takes integer values. So in summary, we have proved the following. 7.50. There is a feasible circulation with demands the set dV in G, even only if the maximum S star T star flow in G prime has value D, if all capacities and demands in G are integers, and there is a feasible circulation, then there is a feasible circulation that is integer valued. At the end of section 7.5, we use the max flow mean cut theorem to derive the characterization 7.40 of bipartite graphs that do not have perfect matchings. We can give an analogous characterization for graphs that do not have a feasible circulation. The characterization uses the notion of a cut adapted to the present setting. In the context of circulation problems with demands, a cut AB is any partition of the node set V into two sets with no restriction on which side of the partition the sources and sinks fall. We include the characterization here without a proof. 7.51. The graph G has a feasible circulation with demand the set dV, if and only if for all cuts AB, the summations of dV summing for all V in B is less than or equals to C of AB. It is important to note that our network has only a single kind of flow. Although the flow is supplied from multiple sources and absorbed at multiple sinks, we cannot place restrictions on which source will supply the flow to which sink. We have to let our algorithm decide this. A harder problem is the multi-commodity flow problem. Here, sink Ti must be supplied with a flow that originated at source Si for each I. We will discuss this issue further in Chapter 11. The problem circulations with the demands and the lower bounds. Finally, let us generalize the previous problem a little. In many applications, we not only want to satisfy demands at various nodes, we also want to force the flow to make use of certain agencies. This can be enforced by placing lower bounds on agencies as well as the usual upper bounds imposed by H capacities. Consider a flow network G equals to VE with a capacity CE and a lower bound LE on each HE. We will assume 0 less than equals to LE less than equals to CE for each E. As before, each node V will also have a demand dV, which can be either positive or negative. We will assume that all demand capacities and the lower bounds are integers. The given quantities have the same meaning as before, and now a lower bound LE means that the flow value on E must be at least LE. Thus, a circulation in our flow network must satisfy the following two conditions. 1. Capacity conditions for each little in capital E. We have LE less than equals to F of E less than equals to CE. 2. Demand conditions. For every little v in capital V, we have F to the in of V minus F to the out of V equals to dV. As before, we wish to decide whether there exists a feasible circulation, one that satisfies these conditions. Designing and analyzing an algorithm with the lower bounds. Our strategy will be to reduce this to the problem of finding a circulation with demands but no lower bounds. We have seen that this later problem, in turn, can be reduced to the standard maximum flow problem. The idea is as follows. We know that on each HE we need to send at least LE units of flow. So suppose that we define an initial circulation F0 simply by F0 of E equals to LE. F0 satisfies all the capacity conditions, both lower and upper bounds, but it presumably does not satisfy all the demand conditions. In particular, F0 to the in of V minus F0 to the out of V is equals to the summations of LE, summing for all E into V minus the summations of LE, summing for all E out of V. Let us denote this quantity by LV. If LV is equals to dV, then we have satisfied the demand condition at V. But if not, then we need to superimpose a circulation F1 on top of F0 that will clear the remaining imbalance at V. So we need F1 to the in of V minus F1 to the out of V equals to dV minus LV. And how much capacity do we have with which to do this? Having already sent LE units of flow on each HE, we have CE minus LE more units to work with. These considerations directly motivate the following construction. Let the graph G' have the same nodes and agencies with the capacities and demands, but no lower bounds. The capacity of HE will be CE minus LE. The demand of node V will be dV minus LV. For example, consider the instance in figure 7.15a. This is the same as the instance we saw in figure 7.13, except that we have now given one of the agencies a lower bound of 2. In part 2 of the figure, we eliminate this lower bound by sending 2 units of flow across the H. This reduces the upper bound on the H and changes the demands at the two ends of H. In the process, it becomes clear that there is no feasible circulation, since after applying the construction, there is a node with a demand of minus 5 and a total of only 4 units of capacity on its outgoing agencies. We now claim that our general construction produces an equivalent instance with the demands but no lower bounds. We can therefore use our algorithm for this later problem. 7.52. There is a feasible circulation
There is
in
a
G
feasible circulation in G if and only if there is a feasible circulation in G prime. If all demands, capacities, and the lower bound in G are integers, and there is a feasible circulation, then there is a feasible circulation that is integer valued.
First, support there is a circulation F prime in G prime. Define the circulation F in G by F of E equals to F prime of E plus LE. Then F satisfies the capacity conditions in G, and F to the in of V minus F to the out of V is equals to the summations of LE plus F prime of E summing for OE into V minus the summations of LE plus F prime of E summing for OE out of V, which is equals to capital LV plus dV minus capital LV, which is equals to dV. So it satisfies the demand conditions in G as well. Conversely, suppose there is a circulation F in G and define a circulation F prime in G prime by F prime of E equals to F of E minus LE. Then F prime satisfies the capacity conditions in G prime, and F prime to the in of V minus F prime to the out of V is equals to the summations of F of E minus LE summing for OE into V minus the summations of F of E minus LE summing for OE out of V, which is equals to dV minus LV. So it satisfies the demand conditions in G prime as well.